students, welcome back to Wisdom Academy YouTube channel. Today we are going to start the second chapter of physics, that is electrostatic potential and capacitance, or electric potential and capacitance. So in the previous chapter we have learned about the electric charges and field, where you saw what is Coulomb's law, you saw electric field due to a point charge, system of charges, you saw about dipole, electric field due to a dipole in axial point, equatorial point, you learned about electric lines of forces, then you learned about Gauss law, flux and application of Gauss law. Second chapter is the continuation of the first chapter. Both of them falls in the category of electrostatics. So here we will learn about electric potential and capacitance. Electric potential is a term which is a very important characteristic property of any point in a field. Like how electric field was there, it was very important characteristic. Same way, electric potential is also a very important characteristic of any point in a field. What is the electric potential? You can just write a definition, then I will tell about it. So electric potential is defined as the amount of work done in moving a unit positive charge from one point to another point in an electric field. I will repeat once again. Electric potential is defined as the work done in moving a unit positive charge from one point to another point in an electric field. Let us see mathematically how it is found. So let me assume that there is a charge kept Q at this point. Now definitely this charge will have a field around it. It will have electric field, radially outwards it will have electric field. If it is considered to be a positive charge, then it will have an electric field radially around it, right? So suppose I have a charge here, let this be point X and let this be point Y. I want to move the charge from X to Y. So at X, suppose the charge is kept, definitely at X when it is kept, it will experience a force. Which direction? In this direction, isn't it? Electrostatic force of repulsion, because plus and plus, I am giving a test positive charge, it will be getting a repulsive force in this direction. What you do, actually if you don't move and let it be static itself, we have to do some work for doing that, isn't it? What I am doing, I am trying to move it from X to Y. Definitely you need to do some work in moving the charge from X to Y, isn't it? So that work done per unit charge is known as the potential difference. I should not say electric potential because that will be little different. I will say it as potential difference. So whatever definition you wrote now, you can please change that electric potential to potential difference. So I will once again tell that potential difference of any 2 points is defined as the amount of work done in moving the charge from one point to another point in an electric field. So write that as potential difference. So the potential difference will be equal to what is the potential at X minus potential at Y. So Vx minus Vy, and that is equal to work done during this process divided by charge. So work done per unit charge is also known as potential difference. So what is the SI unit of work done? SI unit of work done is joule, and for charge it is coulomb. So 1 joule per 1 coulomb is known as 1 volt. So 1 volt, it comes after the name of a scientist, Alexander of Volta, and so 1 volt is defined as 1 joule by 1 coulomb. So 1 volt is that potential difference which is present between two charges if 1 joule of work is done to move 1 coulomb of charge from one point to another point. That is potential difference. Then what is electric potential? Electric potential is the amount of work done in moving this charge from infinite to that point. I will tell in detail about that in some time. So I will repeat once again. Electric potential, how will you write? You wrote a potential difference as it is the amount of work done in moving a charge from one point to another point in the influence of an electric field. Electric potential will be defined as the amount of work done in moving a unit positive charge from infinite to that point in the influence of an electric field. And one more thing I'll tell you, generally at a point very far away, at infinite, we take the potential to be 0 at that point. So if this point, if x is far away, then v at x will become equal to 0. So what will be the v? Then v will be equal to vx minus vy, isn't it? So, or I should write here as vy minus vx. I'm sorry, I'll tell you why vy minus vx, because potential at y will be more and here it will be less. Why I'm saying like that? See, when you kept the charge here, you are doing some work in moving it here, here. Now the amount of work you're doing will be definitely more at this point, because here you came near to it, and since distance reduced, the force of repulsion would be increased. So this minus this, higher potential minus lower potential, was the potential difference. So what will be the electric potential then? Since Vx became 0, it will be only Vy. So Vy, that is equal to work done per unit charge. So electric potential is defined for a point, whereas potential difference is for 2 points. I hope you're understanding it. Electric potential is the potential difference between 2 points, whereas electric potential is only for 1 point. That is the amount of work done in bringing the unit positive charge from infinite to that point. So electric potential of y will be the amount of work done in bringing a charge from infinity to this point. I hope you are clear in this. So that is the difference between electric potential and potential difference. Now we will try to find out the electric potential due to a point charge. We will find the mathematical expression for that. What is the potential due to a point charge? So let me take a point charge for that. Let it be Q here. Place at any location. Then what I want to find? I want to find potential at a distance. Let me take the distance somewhere here on its line, and let that distance be r distance away from that point, and let me name this point as P. So at the point P, I wish to find what is electric potential. So by the definition of electric potential, I already know electric potential at P will be the amount of work done in bringing the charge from infinite to this point P in the influence of this electric field. I hope you have understood what I have told in the previous time itself. So now for finding the mathematical expression for it, what I will do, along the same line of action, at any point I will place a test charge Q0. Let that point be at a distance of x from it. So at a distance of x from this point Q, I have kept a test charge. Now what is the electrostatic force of repulsion between this Q and Q0? By Coulomb's law we know it is K Q Q0 by r square. If I am writing the vector, I can write r cap also. And what is the direction? It is directed away from Q0. I hope you understand what I have written here. So why it is directed away from Q0? Because of the repulsive force acting in this direction. Am I right? Right. So F will be equal to K Q Q0 by, I should not write r square. I'm sorry, it is x square, and here you will have x cap. So x cap is directed away from the charge. Now what I'm going to do, I'm going to move this test positive charge from this point A to a point B. Okay, I will try to find what is the work done. For moving a very small distance, let the distance itself be dx. In moving the small distance dx, I will find the small work done dw, and then I will integrate within the limits. Limit is from infinite to this point r, and I will get the whole expression of electric potential. So once again I am repeating, I will move this test charge from A to B, which is at a very near distance from it. So for a very small distance, I will find a small work done. Then I will integrate in the limits from lower limit to upper limit, that is from infinite to that r, and I will get the expression of electric potential at the point P. So find for that small work done dw, this will be equal to F dot dx, isn't it? So F dot dx means what is the force and what is the displacement, that is work done, and that is equal to F dx cos theta, F dx cos. What is the angle between them? See, dx is in this direction, F is in that direction, so angle between them is 180 degree. Cos 180 is -1, so I can write minus F dx. That small work done dw, it came to be minus f dx. Now to find the complete work done, I integrate on both sides. So I'll integrate from 0 to w, the small work done, and integration minus f dx. From what limit to what limit? From infinity to r. Because from infinite I want to find till r, that is the definition of electric potential. This has come by definition of electric potential. Now let us put the values. F we already know, minus integration of k q q naught by x square and dx comes here. Am I right? So this is the limit is infinite to r. Now k and q naught can come outside, so I get the value as w is equal to integration infinite to r, and I am taking this thing outside, that k, q and q naught, and what remains inside is minus 1 by x square dx. Minus is also there. So 1 by x square dx is minus 1 by x integration. So I'll get minus k q naught into, after integrating I'll get minus 1 by x, and the limit is from infinite to r. Now this minus becomes plus. So minus becomes plus. So I get k q naught 1 to x, limit infinity to r. Okay, so now I'll get the work done as k q naught. First I'll put the upper limit 1 by r minus 1 by infinity, and we know that 1 by infinity is 0, so I get work done is equal to k q naught by r. This is the work done in moving the charge from infinite to this point. And this is the work done I have got. This is not electric potential, this is the work done. And electric potential, by definition of it is work done per unit charge. So electric potential V is work done per unit charge. This charge I will keep, so it will be equal to k q naught by r, and q naught will come, these two will get cancelled. So I got the expression of potential as k q by r. This is the electric potential at this point. Mind that electric potential is a scalar quantity. Why it is scalar quantity? Since it is a work done, and work done being a scalar quantity, it will also be a scalar quantity. Later you will find that this work done is stored as a potential energy, that you will learn in the upcoming classes. So now we have found the electric potential due to a point charge, and the value has come to be V is equal to k into q by r. From here one more thing we are knowing. What we are knowing? That electric potential is inverse of the distance. So electric potential at a point from the charge will be inversely proportional to distance. That means if we go far from the charge, electric potential will keep on reducing. That's why I said you electric potential at infinite will be taken as 0, because 1 by infinite will come as 0. So electric potential is inversely proportional to the distance from the charge from where we are counting. Please keep this in your mind, because electric field was proportional to square of distance. You remember, electric field was proportional to square of distance, but this is proportional to inverse of distance. So the graph of electric potential will be inverse graph, and graph of electric field will be a square inverse graph, or we'll say it as quadratic graph, right? So this graph will be parabolic in nature, and this will be inverse. Actually both will be almost same. If I draw, it will be like this, another thing will be like this, and I'll say one thing to you, that at that particular point they will meet. You know at which point? When r is equal to 1. Don't you think they will be same? Because see, E was equal to k into q by r square, V is equal to k into q by r. So 1 square and 1 are same. So at point r is equal to 1 units, at point r is equal to 1 units, remember that E at this point, E will be equal to V. That I will tell you what is the relationship between electric field and the potential in the upcoming session. I will tell you, but now you understand that at 1 unit electric field and potential will have same magnitude. Now let us see what is the electric potential due to an electric dipole. So I hope you remember what is dipole. Dipole is the arrangement of two equal and opposite charge placed at a very small distance, and we took it as 2D generally, right? So again, actually any dipole will have two cases, at one axial point and at an equatorial point. So both we will see now, and again this is very important for the examination, and don't get confused between the electric field due to dipole, electric potential to dipole. Both are different things. See, electric field was a vector quantity, electric potential is a scalar quantity. Let us find that. So let us assume there is a dipole like this with minus q and plus q, and again the distance of separation is 2D between them. The distance between them is from here to here, it is 2D. Now axial point means in its line of action, somewhere here, let that be the point, and from the center of the dipole it is taken as r. You remember, this was D, this was D, and this was R. Let this point be P, and we want to find the electric potential at P. So here, since it is scalar quantity, potential due to the first, potential due to the second charge. So net potential V will be equal to V minus Q plus V plus Q. So remember that being a scalar quantity, it will be just algebraically added. So now see, what is V due to minus Q? It is K into minus Q by R. Not R, R plus A, R plus D. And what about plus Q? K into Q by R minus D. So now take this is common, KQ as common. So I get here as if I take right like this, so it will be down will have R plus D into R minus D, and what we will have above? We will have above as R plus D minus R minus D. So when you solve this, you will get K into Q, this R will get cancelled, and D minus 2D will become K into Q into 2D by this will become R square minus A square potential. So potential due to axial point, what we got? See, what is Q into 2D? This is called as dipole moment P. So it was K into P by R square minus A square. And if R is much more than D, actually it is D not A, R is much more than D, then V at axial point will be equal to K into P by R square. So remember that in equatorial axial point there it was different thing, it is K into 2P by R cube. Here it is K into P by R square. Let us see for equatorial point. So the dipole is kept like this, minus Q and plus Q, and from the perpendicular bisector, let this point be taken as R, this is A, and at this point P, this will be equal to R square plus A square, this will also be equal to R square plus A square, and I'm going to find what is the electric potential at T. Same way, V due to equatorial point will be equal to V minus Q plus V plus Q. So what will be V minus Q at this point due to this charge? It will be K into Q by R. So K into Q is minus Q by R. R is root over R square plus A square, and this will be K into plus Q root over R square plus A square. Both will get cancelled out, and we get equatorial field, equatorial point V as 0. So remember, electric field due to an axial point due to electric dipole, we got K into 2P by R cube, and equatorial we got K into P by R cube. Here we have got at axial point K into P by R square, and here we have got it to be 0. So this, keep it in mind, don't get confused between V axial and V equatorial. So in today's session, what we have learned? We have learned what is the potential difference, what is electric potential. We also derived what is the electric potential due to a single point charge. Then we derived electric potential due to a dipole at an axial point and an equatorial point. So in the next video, we will see next part of this chapter. Thank you very much.